As you guys are looking at notes where we left off yesterday, do you have any questions about how we got A, B, C, and D, E, F? Any questions about how we got them? Did you guys get down the idea? I'm going to do like a different color highlighter. Down the idea that when we're going, say, a radius of 2, that we take the second tick mark on the Y, the second tick mark on the X, rotate, and then we find the intersection. Does that make sense? As to why A is where it is. It's on the 45-degree line. Like have it to it. Now, if you guys really want to, I guess we can get really good at drawing circles and do lots of those circles and make these small. So we get messy if we try to do that, which is why we only show the circles that we need. And that's way more practical too. So you have to do polar graph. You don't necessarily want to go to your computer and print out the polar graph from some random mathgraphs website. And then have all the nice circles drawn there for you. You could, but you don't have to. So A, B, C, D, E, F. So let's go ahead and let me give you guys a few more points. And I want you guys to go ahead and make one more graph, just because the other one's going to be a bit more involved. But remember, you don't have to make the whole thing. Let me go back. You guys tell me, what did I want you to make yesterday?
45-degree one.
45, yeah, but I'd probably start with
Just the up and down.
the X and the Y, right?
Yeah.
Start with what we would call, no, you're okay. Start with what we would call the polar axis and then the y-axis. Then, yeah, the 45, and that's in both quadrants, yeah? The 45s, the 30s, and the 60s. If you were to have something like a 15-degree, you would just kind of approximate. That's definitely going the wrong direction. And we have them going the other direction as well. Just kind of thinking of you in a circle. And then just tick marks, right? Okay. As you guys are getting this set up, I'm going to finish my tick marks and then let me make a little table that I want you guys to graph. One more time, we didn't get to talk about this a lot yesterday. Why are they called polar graphs? I said something about the north and south, right? Do these somewhat correspond to latitudes and longitudes?
Yes, a little bit.
Could be like you're looking down on the earth, up on the earth. Up on a representation of the earth. With latitudes and longitudes. Which, since the earth is circular, would not be a rectangular system where all the grids are just little rectangles. Instead, it'd be more like this.
Oh.
In the sense of the concentric circles going out from the pole. And then if you look at these, are these perfect rectangles? No. They have arc lengths and things like that. Okay, the little table I want you guys to try to graph is the following. Let's see. We have R's and betas. Let me give you an equation. Let's have a little bit of fun with this. What if I was to give you R is equal to, and you haven't seen much of these yet, let's do 1 minus 2 sine of theta. As you graph this, an equation. I'm going to give you a table. I'm not going to make you guys solve. If I made you guys solve, that'd be my section 10.8. I'm trying to show you a very common polar graph. You guys have already seen the rose, the flowery one. We did that one in class. I think we did like a 5-petaled one. We can make it like 4-petaled or 3-petaled or 7-petaled. The even petals, I think, double. So if there's a 2 theta, there are 4 petals. The odd numbers stay the same. If there's a 5 theta, there's 5 petals. I'm going to show you a different type of common polar graph. polar graphs, theta is like the x in the sense of it is the independent variable, r is like the y in the sense of it's the dependent variable. So I would plug in, let's see, I'll plug in 0. Plug in sine is nice at pi over 3. Sine is nice at pi over 2. Sine is nice at 2 pi over 3. Sine is nice at pi. I'll do a couple more. 4 pi over 3. 3 pi over 2. This might not give the entire graph. Hopefully it gives you an idea. Long story short, in my head really fast, I'm just going to be plugging in these values and getting numbers out. So sine of 0 is 0. 1 minus 0 is 1. Sine of pi over 3 is 1 half times 2 is 1. 1 minus 1 is 0. Sine of pi over 2 is 1. Negative 2 times 1 is negative. Oh, plus 1 is negative 1. Sine of, wait a minute, sine, I'm doing cosines in my head, so change real quick to pi over 6s. I assume someone would have caught me eventually. I'm doing pi over 6s in my head, not pi over 3s. I apologize. Sine of pi over 3 is like root 3 over 2. Ugh, that's a decimal. Sine of pi over 6 is 1 half, times 2 is 1. It's 0 again. Sine of pi, yeah. Sine of pi is 0. 1 minus 0 is 1. Sine of 7 pi over 6 is negative 1 half. Times negative 2 is positive 1 half. 2. And sine of 3 pi over 2 is negative 1. Times negative 2 is positive 2 plus 1. Okay. Thank you guys for giving me a second. I want to show you a particular type of graph. So I wanted to give you an equation for it. Just so you see a polar equation. That's something that you would plug into your calculator and y equals. And I did put the angles in radians because you might see them in radians instead of degrees. Now take those points and graph those points. They'd technically be written r and then theta. So the first one would be written not 0, 1, but it'd be written 1, 0. Polar's kind of backwards that way. First point, 1, 0. Second point, 0, pi over 6. Third point, negative 1, pi over 2. Let's see if you can get them. Graph, and then the second question is, can you figure out how to connect the points? Can you figure out how to connect the points? Graph the points in order. No. R is 0 when theta is pi over 6.
That's 5 pi over 6.
So sine of pi over 6,
That's the table. I can't tell this. Like, what's the second?
pi over 6.
Oh, pi.
I thought you said sine of pi over 6. You just said pi over 6. It does say pi over 6.
Yeah. So you say sine.
So you would plug it in. Sine of pi over 6 is 1 half. 1 half times 2 is 1. 1 minus 1 is 0. Yeah. So theta is pi over 6. Plug it in. R ends up being. I did some quick unit circle stuff. Just to get us started, in case you guys got one. First point says it helps. We'll do A, B, C, D, that way you guys can see it. You don't have to write this if you're showing you. Once you guys finish trying to graph the points and thinking about how they connect, let's go to your graphic calculators and try plugging it in formula. sure as to what's going on. Remember, the window can get kind of messed up. But if you guys are still kind of stuck how to start, remember, for the very first point, the angle is 0, which is along this line, and I'm going out 1 towards the 0. So there's my point A. 0 is my angle for point A. 0 radians, 0 degrees, same one. R is a positive 1, so I'm going 1 towards the 0. For pi over 6, 0 is my radius. So I go B. So even though pi over 6 would be this 30 degree, the radius is 0, so I'm not going out at all. I'm staying on the pole. What do you guys do for -1 pi over 2? Because here's pi over 2 line, right? What's -1? One in the opposite direction. Yeah, Ashley's pointing down. Instead of going up towards 90, instead of going up towards pi over 2, I'm going 1 backwards. And C should be down. So far we've gone somehow from A to B to C, but if you guys realized from yesterday, polar doesn't do straight lines usually. Polar does some sort of curvy from A to B to A to B to C. Guess it could have gone the other way, but that's awkward to get to C. It must be curving. D at 5 pi over 6, you're over here. Back at 0 again. At pi, you're out 1. So we're back at, for D, we're back in the middle again, so B and D.
Why would you move
For E, because pi is 180 degrees, right? Positive 1 means go 1 towards pi. Does that make sense? So go 1 towards the angle, towards 1. Or, ooh, I didn't write 7 pi over 6. Oops. Maybe that's stuck in there. 7 pi over 6, I think that's this one, right? 30 degrees down. Wait, going out 2. So here's my F. 7 pi over 6 would be 30 degrees down. Going out 2. 2 tick mark to 2 tick mark. I should say -2 to -2. Going out 2 towards 7 pi over 6. Yeah.
If we have to graph these, will you already give us a polar graph? Or are we going to have to draw one?
For you guys, I'll probably give you one. For honors, they kind of have to draw their own, like how you guys are doing. And they actually have to come up with the equations and plug in the tables. That's to me. But you guys, I'll probably give a polar graph. Because it'll make it faster. You still need to know how to go forwards, backwards, that sort of thing, but you don't have to worry about the lines. What are we missing? Oh, G. Where's 3 pi over 2? What angle is that? 270. And positive means we're going towards 270 or away from 270? Towards 270, which is down, but it's towards 270. And how many? Towards? No. Yeah, it does look weird. Unless you realize, and don't worry, not necessarily it's not all unless you realize that you always rotate to the points. If you always rotate to the points, maybe you could see how we should finish.
It's so hard. Not to
Are you-
Kind of a hard.
more than that. And that would be correct.
There actually is one called a cardioid, and the cardioid comes to the pole. It doesn't do that little inner loopy thing, it just comes to the pole and has like a heart top. Cardioid, cardiac. That makes sense, right? Heart. So there's one called a cardioid. But it's actually a special type of a more broader type of polar, which is called a limassol. A limassol. It's French, so it has a little interpreter. I don't know what that's called. Is that a little accent called in French?
So that makes an S sound.
Go down. It's like an S, right?
Yeah. Like a facade or something.
It's a limassol. According to what I've read, I don't know if it's actually a new book this year, if it's in last year, it's like not last year, my old book. It said limassol means snail in French, not the food. Not the food. But a snail. And the reason being, I can flip mine upside down as opposed to my smartboard, I can't flip that upside down, or the projection. Anyways, if you look at it, it looks kind of interesting. Here's a little snail, here's your shell, back here. And here's a little snail in the front. Anyway, it's called a limassol. Let me undo. Let's make sure we're able to get our graphing calculator, because we're going to use those tomorrow, right?
Do you have to know that?
You never know, it might show up somewhere, but it's not a big idea. I mean, it is a big idea of polar, and not making you memorize all the shapes though. In our graphing calculators, if you guys went to polar mode and plugged in 1 minus 2 sine theta. I'm guessing Zoom standard?
Yeah.
Oh, that's right, he's a little baby guy. Oh. Hey, I did do pretty good with my snail, huh?
Nice.
And if we were to zoom in, maybe even zoom square, we could see him maybe even a little bit better. But we have our little inner loop, that's a little like body of the snail, he's upside down.
Oh no.
We almost got it. We could do zoom square to make it a little bit more proper. I could do zoom fit, Kayla, but it always kind of worries me as to what's going to show up. I'm just going to do -4. Then I'm going to do zoom square and see what happens. Looks pretty good. Did anybody not get this? Because there are things that your calculator can do that are kind of funky and can mess up. Yeah. No, you're okay. Weird things can happen. I'm currently in degree mode, which is why mine looked degree-ish. 0 to 360, taking bigger steps. Remember my analogy of if I was going from here to the table, I could take 80 steps and it wouldn't take long. If I was going from here to last, and I literally would rather take full strides. Same thing here. The step is how many steps to take from 0 to 360. I can go by 5s or 7s or whatever. That's okay, but if you were in radians, this window would be very inappropriate. If you guys want to check it out, if you were in radians, how would this look?
Awful.
Not like a snail. I mean, maybe you can see a snail in there somewhere. Huh. You can see the snail in there somewhere. But it's doing all sorts of funky stuff.
It's just making like a circle.
Well, yeah, look, sort of is.
Oh, I guess.
But it's not exactly perfect. The point being, in radians, I need to go from 0 to 6.28 to make 1 revolution. So 360 is way too big. It should have been too high. And 7.5 was taking big steps and saying, where are you at this point? Where are you at this point? But you're missing all the in-betweens. You do all the in-betweens.
Let's do it,
It can look good as long as your window doesn't look like a degree window. If your window looks like a radian window with 0 to 6.28 and 0.1 or 0.2, then you should see the same picture as the degree window in the degree mode. Sam, did you get worked out of it? Yeah. Okay. Or there or not. Oh, no, sorry, the pull up. Yeah, pull up. What is it called? Pull out cover doors? Let's keep going. Oh my goodness. We need some algebraic stuff. So here's the last idea in 10 seconds. Not just the points and graphs. The graphs are important, but I'm not making you really stress about polar graphs. I could see if I have pictures of polar graphs. Show you all the special types. I want to do a picture. I'll show it to you in a second after you guys get this page done. We're going to fill in this page with, now the name of the game is converting. We did this in parametric. To convert parametric equations to something we're more used to, rectangular, we would eliminate the parameter. To convert polar equations, we can't just eliminate the parameter. Because in polar, we don't have x equals and y equals. In parametric, we still had x's and y's, they were just in different places, and we had to kind of maneuver, substitute in order to get x's and y's in one equation and the t's out, or the theta's out. But in polar, we have r's and betas. How do they relate to x's and y's? That's the question we need to answer for that in class. That's the question we need to answer for that in class. And it all comes down to this triangle. This triangle that we looked at, I think, really quickly at the beginning of notes. We need to kind of fill in that. This triangle of, for any point that we're now seeing as r and theta, where theta is like a rotation, how much you rotate, what angle you rotate to, when you're going positive angle, positive angle or negative angle, how much you're rotating, and then r is how much you're going out along a diagonal, along the angle line. That should relate to rectangular, the old-fashioned way of getting there, which was going over an x and up a y. We've seen this triangle a few times this year. It's been applied in a lot of different ways. It was applied in vectors, and we were talking about magnitudes and directions. Oh, we're not stressing out too much about that. Skip in chapter 11, three-dimensional vectors. Could be fun if this was physics. Or pre-physics. We do a little bit of that. But now it's being applied to polar, because now we have these points that are completely defined in terms of rotation and, in a sense, magnitude or directed distance. But how does it correspond, or how does it relate to x's and y's? So how to convert from polar to rectangular, rectangular to polar. We're going to need to use, guys, I technically have these little categories as in, okay, polar to rectangular, rectangular to polar. I actually just want you guys to think about converting in general. You might have written that, and that's not bad. That's not bad. But let's do this, because you guys don't know about that. I'm just going to show you formulas. I'm not going to put them in one category or another. That sometimes messes kids up. So like, no, that only works if you're going from polar to rectangular. And sometimes you use them in different situations. So we should pull out a few of these relationships. And we'll just say they help, or they can be helpful in either case, going from polar to rectangular or rectangular to polar. First of all, Pythagorean theorem, we can say x squared plus y squared is r squared. So we can relate the radius with x's and y's with Pythagorean theorem because they're all sides. We can relate, well, once I start getting to trig, it's a little bit tricky. Let me use one first. Tangent of theta is equal to y over x. So theta relates to y and x, in that y is opposite, x is adjacent, so I can just use tangent. So similarly, from that one, I could say, kind of like a little subset of that, that's not a marker. I could say theta is equal to, I'm not going to say equal to, it depends on the picture in the quadrant. I'm going to say for theta, we need to use tangent inverse. So if we have x's and y's, we can plug into Pythagorean to find r. If we have x's and y's, we can plug into tangent inverse to find theta. But we might need to think about the picture as far as what quadrant is appropriate for the problem that we have. We've done that a bit before in other cases as well. Vectors, complex numbers, stuff like that. If we're talking about trig, well, we have tangent. These ones aren't quite as nice. I'm going to write them up above. We can also talk about, though, all the other trig, but I'm just going to focus for a second on sine and cosine. Cosine, what's the ratio of sides for cosine? Adjacent and hypotenuse. So I can say cosine is x over r, but we're not going to usually have an x and an r together. What's a little more common is we're going to have r and theta and need x. So we can multiply r to the other side and have this formula x equals r cosine theta, which kind of sounds like something from vectors as well. And then for sine of theta, sine is opposite or y over r, so very similarly. I can also say if I have r and theta, I can solve for sine. But in vectors, we were using magnitude cosine theta and magnitude sine theta in order to find the horizontal and vertical components. So the same triangle, just applied a little bit differently in this case. Same basic relationships. So we pretty much have 4 different main formulas: the Pythagorean theorem, tangent, and, well, how we're going to use that tangent formula. One for x and one for y. R cosine theta and r sine theta. Little bugs. Stop them. Now, let me go ahead and real quick before we just basically focus on algebra converting back and forth for the rest of the lesson. Let me show you, I said I had some of those pictures of the main polar curves. We'll come right back. Just to give you an idea, you don't have to memorize them. You don't have to be able to graph them all or name them all necessarily. Especially in negative Precalc, we're just kind of introducing them. But these are all the different types of limasomes. We have a limacome with an inner loop. We have one, see what I said about the cardioid? He's technically a limasome, except what's different and why they call him a cardioid is right that little cusp right there. We have a dimpled limasome that comes in a little bit, but not enough to make it all the way to the pole. And then we have a convex limasome, which kind of is flat, doesn't actually come in at all. So we have limasomes, different types. They could be like oriented differently. We saw one that was oriented down. We'll see how it's upside down. There are also the ones that you guys saw, the roses, with different petals. The roses with different petals. And if you guys notice what I was saying, like if you do throw in like a 1 theta or a 3 theta or a 5 theta, you're going to have those odd numbered of petals. But if you throw in an even number, you're going to have twice as many. But there are different roses, and I know they're like daisies, right? The girls are taking right now. Guys are not good. But they technically are mathematically called roses. And then last but not least, these aren't the only ones. You can have lines in polar. You can have hyperbolas in polar. If you guys are playing your calculator with 10-7, hopefully you'll see some of those. Double ellipses in polar. But you could have circles, and then you could have what we call lemniscates, which are like infinity things. Anyway, just to give you some ideas so that you don't have to graph them all to know what they look like. Those are the main types of polar curves. Let's come back to what we were working on, which was converting. All right, let's go do some examples and see if we can use these formulas, okay? So, from polar to rectangular, points specifically, so not equations yet. What if I was to give you the point, -3, 11 pi over 6. We're going to go from polar to rectangular on that one. You can kind of tell it's polar just by looking at it, but the direction will help as well. Because 11 pi over 6, well, that's an angle. That's a theta. Oh, that must be polar. Rectangular to polar, number 4. Negative root 3 over 3. Sorry, negative root 3. So we're trying to go in this one from an r theta to an xy. So if you look at your formula, see which one is seen to apply. This one from an xy to an r theta. Think of that. What formulas can you use? Are you guys breaking from your English maybe?
We're ditching.
Oh. You're back in break?
Yeah, 10 minutes. We're gonna be back at 11:40.
9:40. Are you going
9:40.
to
Yeah.
House
We just got 12
Done.
minutes.
You're fine to just put down minutes. Go team. I'm done. It's okay.
Let me beat it up. Or you kick it for
I
you.
don't know why it's moved that way. I think Jeremy was sitting at this morning. That's fun.
Remember when I came in last year for my after breaking my push there? And I was freaking out.
No, I probably
Good
remember
time.
when I lived here.
You still live in here?
I still do.
I know. Okay,
Probably Jordan.
question. Did anybody think that you're supposed to look at the formulas and see what seems to apply? Anything that seems to apply?
Yeah.
Okay, but I want X, I want Y. What formula are you guys thinking?
-3 sine by 6.
Yeah, I think I like the one that says, hey, I'll give you X, right? The one that says, hey, I'll give you X is X equals R cosine theta. Let me try. And the one that says, hey, I'll give you Y. Shoot, I want X, I want Y, right? So then we can use those two formulas. It's okay. Find X, R cosine theta. Define Y, R sine theta. Okay. And in order to plug in, we have to think about our unit circle anyway. So if we just take a second and say, all right, 11 pi over 6, who's already figured out what quadrant? Yes, I'll let you use your calculators tomorrow, but if the multiple choice has like radical things, maybe you might actually think unit circle. Quadrant 4, 11 pi over 6 is right before 2 pi, right before 12 pi over 6. And that would have the coordinate pair of, let's see, X would be over a lot, 3 over 2, down a little, -1. So we go to plug in. You can go ahead and say, all right, what do we got? -3 cosine is the X, which would be √3 over 2. Sine would be the Y, which would be -1/2. And we're making a point out of it. So the X is going to be -3 √3 over 2. And the Y is going to be 3 over 2. Now I do have a question for you once you find this point. What point is this? What quadrant is this point in? Think about X's and Y's, X's and negatives, Y's and Y's. Quadrant 2. So you go over somewhat, and then you go up somewhat. Well, wait a minute, isn't that like the total opposite place it's supposed to be? How would we graph this polar point? You would look at the angle 11 pi over 6, but then what would we do? We would go backwards. Does that make sense? So this is exactly where it's supposed to be. My math has checked out. It's not, I would say it's never a bad idea. It's never a bad idea just to double check and make sure that all your math is working out. And that's especially helpful in the next problem. The next problem, does anybody get to look ahead and think about, if I have an X and have a Y, how can I start getting R's and Theta's? Yeah, we can use that tangent inverse of Y over X thing. That's supposed to help with my theta in the third column. And then with R, what do you guys think?
Oh, that's great.
Yeah, let's use Pythagorean again. I'm going to go ahead and square a root because I want the R by itself to get R and theta. I can go ahead and plug in and say, okay, so my R is going to equal, I could say plus or minus square root. Maybe we'll need to narrow that down in a second. We have X squared, which would be -√3 squared, plus Y squared, which would be √3 squared, which equals plus or minus. The nice thing about square roots and squares, a negative times negative is a positive. Don't even worry about that. It'll be 3. And the square root and square will just be 3 again. So right now we have R is equal to plus or minus √6. That's funny, but it's right. My theta, I'm going to use tangent inverse. And which one's my Y again?
3.
√3, the positive. Good. And which one's my X? -3. And just a few of you are like, hey, wait, I can do this without a calculator because don't they reduce? You just get -1. Ooh, where's tangent 1? Square root of 3 over 3, 1 square root of 3. Get 1. 1's in the middle. 45. But this is a -1. Ah, it's going to be a 45. When is tangent negative? In what quadrant? It could be the fourth or it could be the second. Because in 1, positive over positive tangent, and 3, negative over negative is that positive. So I have either quadrants 1 or 4. Now, technically, tangent inverse would almost always choose, like if you were to do it in your calculator, this would get for you -45 or -pi/4. Let me do it in degrees just for the sake of you guys would see degrees easier in your calculator, faster than radians. But the problem is we have to consider our point and say, wait a minute, is this accurate to my picture? So kiddos, if we were to graph, what quadrant do we need to be in if our X is negative and our Y is positive? The second quadrant, yeah. we need to go negative root 3, positive root 3. You need to be here. So do I want negative 45? What would be the easier angle to choose? What angle is the 45 in the second quadrant? AKA 90 plus 45. So the easier angle would be 135, but let me show you options real quick. So we have some combinations, okay? We have that it's some sort of 45 in the second or the fourth quadrant. Let me show you a few polar points, because remember how there are infinitely many polar points? One polar point could be, the R goes first, positive root 6 and 135 degrees, because that would say turn 135 and go out towards 135. Come on, root 6. But you could also, if you wanted, you could go negative 45 and go backwards root 6. So you could have negative 45 and go backwards root 6. That would be the exact same point. You could go, let's see, 315, which would be going this way, backwards 6. So here's the long story short. The struggle with going from rectangular to polars, there could be tons of different ways of making polar points. You just have to make sure whichever one you decide to choose, or maybe they ask you for more than one, that it actually matches up with the location that you need it to be. Does that make sense? If you did negative 45, you couldn't have it going this direction, or else you'd have it wrong. All right, kiddos, so we have converted points. There's really just two more types that I want you to do and we'll be done. We'll do one each. But I did promise that I would stop and pause for a second to let you guys know about the quiz tomorrow before we do these last two examples. So the last two we need to do are equation conversions. We'll go over homework questions real fast at the beginning of tomorrow. Let me go ahead and get a special, what haven't I used? A green highlighter? I never use that. These equations you need to be familiar with. My hint would know the triangle, and all the equations come out of that. Know how to graph polar points, and as Ricky already asked, I will give you a polar graph, a nice with all the circles and everything that you can use. Know how to graph polar points. And then the other thing was know how to convert points, rectangular, polar, rectangular, and equations. From parametric in 10.6, going from rectangular to parametric is pretty easy, but you might need to review that. I'm not going to make you memorize like the parametric equations. I'm not going to make you do that. But to eliminate the parameter, there are different types of problems that show up, so that would be a good one to look at. There are different ways of eliminating the parameter. And then let me just put a little star by this example. Being able to graph a parametric with a table and show orientation as far as what direction it's headed, and knowing that they stop. The parametric curve begins and ends. It doesn't go on forever. And then I think besides that, being able to use your calculator, that's pretty much the entire quiz. So let's go back to converting equations real quick. Just so you guys have a couple examples. I'll do like one each. For number 75, they give us, let me do number 82, a little bit, not harder, but different. 2xy equals 1. And then I'm just going to write down the next example real fast. 95 or 109, which one do I want to do? Let's do, not 109. That's even harder than 295, which is theta equals 2 pi. Okay. For number 82, guys, those two equations, the ones that we just started, is there anything for x or for y that can get us r's and thetas? Yeah. X we can substitute for, and y we can substitute for. What can we substitute x for? I was trying to plug in for x, something with r's and thetas. We have x's, y's, we want r's, thetas. What's that formula on that page, x equals,
Cosine theta.
and y equals.
R sine theta. R sine theta.
Now, technically, you're right. If it was a long answer, I suppose you could stop there. It's kind of messy. Might be a little easier to do something like 2r squared cosine theta sine theta equals 1. And usually in polar, r equals f of theta, aka we get r alone. So if we get r alone, we would go ahead and like divide both sides by the 2. We have r squared equals 1 over 2 cosine sine. If we want to be super snazzy, I suppose we could do plus or minus square root. We could even do like 1 over cosine is secant. 1 over sine is cosecant. There's a lot of different ways of writing them. I'm just going to box one of them. Just getting it in terms of r and thetas. And last but not least, is there any equation that uses a theta? No! Can't we substitute theta to be tangent inverse of y over x? I know, pause. How do we get rid of tangent inverse? He's messing up the
And
Guys, I'm going to finish this. It'll be on the video if you want to see it. I'm just letting you guys get on a video getting the notes online. Homework 10-7, do tomorrow. Study specials yet. We'll go over examples and questions just a little bit before the quiz. Nice to try everything. Yeah, you want to get the unit value, right?
oh wait, but then you have tangents. Oh no,
Because I solved for tangent. Does that make sense? I got a number, then I just solved for it.
Oh, you already did tangent too.
Austin, the reason I have tomorrow is because Friday A-Push has their AP, and so I'd have kids gone, and it would just be a mess. So tomorrow's the best day, but if Friday you're here, then here, let's do that this time. If you're going to be gone.
See you, Mr.
Okay.